Well, let's see, it's 5:25 and I don't have any students. Nobody showed up yet. Well, even if nobody shows up, I go ahead and give my lecture anyway, because it's on YouTube later and you can watch it. Now you do have some homework. There's also a makeup lab this Wednesday or Thursday. Thursday is a makeup lab. And there's a student, there's Phoebe. I'm not alone.
Hi.
Hello. I got an email from you and I think I answered you, but I don't remember. Did I answer your email?
Yes, you answered half of it, which is all right.
Well, good. I'm glad I answered it.
Yeah, I had another question that you didn't address, but that's okay.
Well, I guess email me again, maybe.
Okay, that's fine.
Yeah.
I know it gets busy.
Yeah, we get busy. Now, there's a makeup lab, and that is on content. If you go to content, you can pull that up, and everybody's welcome to come to this makeup lab on Thursday. It's our last lab. If you have 10 labs, we only count 10, so if you don't want to come, that's fine. If you already have 10 labs and you like your score you got, that's fine. But it's on content, and the name of it is, I've got it right here, series RLC circuits. That's what the lab is. And this is it for labs. Next a week from Thursday is Thanksgiving holiday week. Well, the holiday is the 25th, 26th, and 27th. But after Thursday, there's no more. We don't get together anymore. It's kind of sad, but that's it. Your final will be online, and it's comprehensive. And it's scheduled. Open book, take home final. Think of it like homework even.
I got a question about class. So is this the last online lecture?
No, we'll have a lecture next Tuesday night, and let me see. Let me look at the calendar here. Coming to an end though. See, now tonight's the 17th, and we'll have a wonderful lecture tonight. I'm going to review you a little bit, and then we'll talk about AC circuits. And then the 24th, we'll meet. And the 1st. But see, let me get my calendar out here. Tonight is Tuesday night, the 17th. 1 week from tonight, we'll meet again. And then we'll meet on the 1st of December, right? Yeah, I think so. December. Yeah. Yeah. And then I think that's going to be it, guys.
Okay.
I think we meet 2 more times. See, today's the 17th. And then there's the 24th. And then there's the 1st of December. The 24th, I plan on having our meeting at 5:30. like always. And that's tonight.
Mm-hmm.
Now there is that makeup lab this Thursday, and we'll meet there and we'll do this makeup lab. But there'll be no more Thursday nights, and then the final is December 10th. Let me see when that is. December 10th. Well, it's on a Thursday. I don't know why it's on a Thursday, but it is. You know, the school has a schedule. The 10th of December is your final becomes available. Let's put it that way. And then you have till Saturday to do it. I don't know. Let me see what it says here. It's due the 13th. That's Saturday. According to this, it's due Saturday. And no, the 13th is Sunday. It's due Sunday the 13th at midnight. Dun, 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 dun. So that's what's left. Not much. Not much left, huh?
Mm-mm.
No. I hope you've learned something. Now, let's have our review now. Let me see if anybody else showed up. Yeah, we got Zach now. Good deal. Zach, we missed you last time. You might want to come to this makeup lab and pick up some lab points. And Nicholas is here. Hi, Nicholas.
Yeah, I didn't have to come to the last one.
Yeah. If you come, you can get some lab points Thursday night. That'd be good. Nicholas, you had some kind of question for me about something recently. Do you remember what it was? You had a,
Well, yeah, I got a question for you, but it's not really for this class.
oh,
So
well, you can email me.
yeah,
I've been pretty bad about reading my emails, but I'll try. Well, I think it's time to start our little review session. I've got a review problem for you now. There's the schedule. We meet tonight. Thursday we'll do our lab. We'll have 2 more meetings. And then that's on Tuesdays. And then on Thursdays, that's it. It's coming to an end. Okay. Now for the review. Here goes. See if you guys remember how to do these. I just made this up myself. This is a 80 volts. That's kind of an odd number. Let's make it 90 volts. You know how you could get a 90 volt battery? Take 10 9-volt batteries and just put them together. You know those little 9-volt batteries? They have a male and a female, and then take the other one and put the female here and the male here, and then you can do this. And then take another one, take the female one here and the male here, artist's rendition of these batteries, and just stack them up like this. And You get the picture. Get 10 of them, and then you connect them. See, this is the negative, and somewhere over here, you'll wind up with a positive, and you've got a 90-volt battery. There you go. Suppose this is 16 Henry, and this is 40 ohms. So that the numbers divide nice, we'll make it 30 ohms. Okay, now when you throw the switch, something's going to happen. And the kind of questions that we could ask, there's all kinds of questions. The first question would be the time constant. I'm going to shut up and you figure the time constant, and then I'll tell you if you're right. Go ahead. Find the time constant. Well, you should be done by now if you remember how to do it. Let me go to one of my wonderful students here. Zach, do you remember how to find the time constant?
Yes, L over R.
Yeah, that's all it is. It's L over R. So what'd you get, Zach?
0.53.
That's what I got. Well, what are the units, Zach?
Seconds.
You got it. Jolly good. Did great. Now we're going to throw that switch, and here I'll ask you some questions. I want you to find find the current. The current. Use a symbol I there. You can use a big I if you want. Usually they have the capital letters for things that are constant. Hey, look, we got Stephen with us. Good deal. Good deal. We got a nice little class here. Usually they have the little letters for things that are changing and the big letters for things that are steady, but it doesn't have to be that way. Find the current. Let's just make something up. Oh, I don't know. I'm just making these questions up. 1.5 seconds after you throw the switch. We're going to throw that switch, and I want you to find the current. Now, you know which way the current goes, it's going to have to go this way. Current is always the motion of positive charge. They leave the battery, and they're going to go around clockwise, and I'm going to shut up, and I want you to find the current 1.5 seconds after you throw the switch. I'll be quiet and let you work. Go for it. Well, anybody think they got that current at the 1.5 seconds after you throw the switch? Well, we'll just bug some of you guys. We'll see here. Stephen, do you think maybe you know what that current is? Stephen didn't answer me.
Yeah, I'm sorry. I only just got
Well, that's
got
okay.
here.
Well, that's
I'm
okay.
not
Take
sure.
your time. We'll just bug somebody else. Nicholas, what do you think? You think you know what?
We got 1.24 amps.
Yeah, that's not what I got, but I'm going to write
No.
it down. You might be right. I might be wrong. How about somebody else? Let's pick on.
I got 2.82.
That's what I got. I got 2.82. Let's write it out. I don't think the 1.34 is right, but see, that's what we're here for. We're here to learn. Okay. What you do is you write your equation, and it goes like this. You do this. There's your equation. And in this case here, this is 90 divided by 30, so that would be 3. And this would be 1.5 over 0.5, bunch of 3s. And if you do that, you get the 2.82. Well, let's do another one, because I want Stephen to get it right this time. But do you all understand that okay?
Mostly, I couldn't figure out which equation to use.
Yeah, I understand. Yeah, but that's the equation. Let me ask you this. I'll ask you some more questions here. When you throw that switch, at the instant you throw the switch at time 0, what's the current in the circuit right at the instant you throw the switch? What do you think?
V equals IR?
Nope.
No. I'm like, I'm wrong.
Do you guys remember my little talk I gave you that these inductors, see, that's an inductor. The symbol is L. Of course, you know resistors, the symbol is R. Inductors, they kind of act like a flywheel. I don't know if you listened to me the last time I gave you this wonderful talk, but see, I've got a grinder in my garage, and the instant I turn on that grinder switch, it's not turning yet. It'll start to turn, and it'll build up. It'll start like that. See, but the instant you turn on the switch, it's not turning. Inductors are like a flywheel or a grinder. They don't just jump instantly turning. No, it takes time for them to crank up. So the current at the instant you throw the switch is 0. So that you'll believe me, put a 0 in here. If that little t is a 0, then you'll have e to the minus 0 over 0.533. You know what that is? That's a 0. E to the 0 is 1. 1 minus 1 is 0. This term is 0. So if you plug in a 0 for t, you'll get 0 for current.
Makes sense now.
Yeah.
Thank you.
You're so very welcome. Here, let's do another one, because I want to make sure you got this. I want you to find the current. Let's find the current at 0.5 seconds. 0.5 seconds. You're going to throw the switch, and a half a second later, what's the current? Go ahead, I'll shut up. You do it. Let's see, I'll pick on somebody else here. I don't want to pick on the same person. I've already asked everybody. We just have 4 people. I'll ask for volunteers. Somebody tell me what you got, the current at 0.5 seconds. Go ahead, be brave. What'd you get?
I got 1.8258.
That's,
1.83.
that's exactly
Yes.
what I got. Yeah, did I hear another yeah?
Yes.
Yeah, good going. Well, we just got the current in the circuit there. Now let me ask you some other stuff. What is the voltage on the resistor at a half a second after you throw the switch? What will the voltage be on the resistor? I'll shut up. Figure it out. Go for it.
What'd you ask for?
I want the voltage on the resistor 1/2 second after you throw the switch. And do you know how to do it? I think I know what it is. I got 54.75 volts. Now, if anybody got that, say, uh-huh. I didn't hear any uh-huhs. Let's pick on Nicholas. Nicholas, do you know how I got that? How did I get that 54 volts?
I don't know.
Did Nicholas say I don't know? Is that what he said?
Yeah.
Nicholas, V equals IR. You know the resistance and you know the current. Now find the voltage. V equals IR. Do you get, Nicholas, do you get 54.75 volts on the resistor?
Uh-huh.
Yeah, now that's what I like to hear. Now, Nicholas, I'm going to ask you a question. You got a 50-50 chance of getting this right. That's a resistor. One end is going to be plus, and one end is going to be minus. But where do I put the plus? Is it over here on the left, or the plus is over here on the right? Nicholas, you got a 50-50 chance of getting this right. Where do I put the plus, and where do I put the minus?
I think the plus goes on the right side.
Yeah, he got it. Now, how come, Nicholas? Why is that?
The side that's hooked up to the positive terminal on the battery.
Yeah, yeah. Well, see, the current's going this way. You throw the switch, you throw that switch. Current's going this way. Current's going this way. Current's going this way. On resistors, If the current's going that way, this end is always positive and this end is always negative. Memorize that. Well, let me ask you some more stuff. There's some room right here. I want you to find the voltage on the inductor. Find the voltage of the inductor, 1/2 second after you throw the switch. I'll shut up and let you find that. Go ahead. And we'll go to my friend, pick on Stephen again. Stephen, what's the voltage on the inductor?
Well, I was actually going to ask, do we know what the resistance on the inductor is?
We don't speak of resistance of inductors, even though we actually measured resistance last Thursday night. This theoretical inductor, Stephen, has no
Right.
resistance at all. Pretend it has no, real inductors do, so we're lying to you. But neglect any resistance and pretend it's pure inductance.
So 0 ohms? Okay,
Yeah,
I'm-
zero ohms. You're right, 0 ohms.
So there'd be 0 voltage there.
Well, see, inductors don't obey Ohm's law for resistors. This law here only works for resistors. The inductor is not a resistor. The voltage on an inductor is given by the changing current. The current has to change to get a voltage in an inductor. But we can still find the voltage on that inductor. Does anybody know how to do it?
Yeah, I have a DT.
Yeah, you subtract.
That's it. You just subtract. So what'd you get, Phoebe?
Sorry, I accidentally moved away to a different page on here. I got to 35.25 volts.
That's what I got. I got 35.2, well, I got 2.4, but let's don't fight over it. Volts. Phoebe got that just by subtracting. Look, Kirchhoff's voltage law still works. You go up 90,
90.
you go down 35.24, you go down 54.75, and the total gets you back to, well, it's 0 total. You know, the sum of the voltages will be 0 as you go all the way around the circuit. That makes sense. Any other comment or question on that? Well, that's enough of review on that. But hey, I think you guys needed that. I got the feeling you needed that. Well, let's talk about the AC circuits. Unless you have a question or a comment, I'm still listening. Okay, well, I'm going to erase this. We had a little review there, and I think you needed it. Okay, now the topic here tonight is AC circuits. And that stands for alternating current. They just call it AC, okay? And when you plug your lamp or your hair trimmer or whatever you're plugging in, or your blender, the voltage kind of looks like this. It's a sinusoidal voltage. That's the way a sine curve looks. Here's voltage, here's time. And this peaks out. I have to stop and think what it peaks out at. It peaks out about 155 volts, and it bottoms out at negative 155 volts. So peak to peak, if you wanted to talk peak to peak, that would be I think 310, wouldn't it? If you added those up, I think so. 310. That's a pretty big voltage difference between the peak there and the trough there. What did I say? 310? Yeah. This time, by the way, keep this, trying to get this even there. This time right here is 1/60th of a second. There are 60 of these in a second. See, I've got a lamp plugged in over there against the wall, and that lamp is plugged in, and this is the voltage that's entering the lamp. It goes up to 155, down to negative 155. This is the, oh, they have a name for it. I guess just the peak voltage, that's the name for it. That's not what they call it, though. They call it the RMS, the root mean square voltage. The RMS voltage is 110. I bet you've heard that, 110. Your dryer is 220. If you have an electric dryer, you plug it into 220. But most of the outlets in your bedroom or kitchen are 110. And we're going to talk about that root mean square here a little later. And see what this is it's got a frequency of 60 hertz. What a hertz is, it's a unit of frequency, and it's if you spell it out, I think that's how you spell hertz. Kind of like the rental car. Is that how they spell the rental car, the hertz?
Yes, I think so.
Is that it? Okay. Well, that's the frequency. Now, they also have an angular frequency that goes like this. It's equal to 2 pi f, and what it is radians per second. I don't know, in school, in high school, when you studied sinusoids, see, this is the graph of 155 sine of omega t. It's a sine graph. What they did was, if you took a circle and you had a particle going around this circle like this, about the middle, oops, it's more like that. Come over here, here's your angle theta, and this right here is your radius, which in this case is going to be 155 volts. And it's rotating around here, spinning around here 60 times a second. And what that is 155 sine of theta. I don't know if that made a lick of sense. But if you had a rotating, it's like a rotating vector. If you had a rotating vector spinning around 60 times a second, see, it would go up, and it would go up, and then it would come down. It would come down and be zero right here. Because see, when theta is 180 degrees, sine of 180 is 0. And then you take this rotating vector here, and when it's down here, you'll get a negative. This is a depiction of this rotating vector. They have a name for that rotating vector. It's called a phasor. This rotating vector here, it's a rotating vector. And it's called a phasor. Now they have voltage phasors, and that's what I'm doing here. They have voltage, but they also can have current phasors. The current's doing the same thing. If you had a resistor, here let's suppose you had this AC voltage connected to a resistor. Here's a resistor. Here's your AC voltage, V sine of omega t. The current would have the same, it would just, it's just going to kind of copy the voltage. It might be a little bigger like this. Here's your current. There you go. See, that red thing could be the current, and the black could be the voltage. They're in phase in a resistor. However, if the resistance was big enough, if the resistor is real big, then the current might be smaller. It might be more like this. See, this is the kind of current that you would get if the resistor had a whole lot of ohms, maybe 2,000 ohms, let's say. But they're in phase. They just sort of copy one another. Resistors and voltages are in phase. That's what we mean by in phase. They peak out together. They bottom out together in resistors. And this business here of this rotating vector that's spinning around, it's called a phasor. And that's a voltage phasor. Well, we can have a current phasor. We just need to paint it red. Paint it red and have that thing spin around 60 times a second. And we got a current phasor. It's really kind of easier to understand this rotating vector than it is this diagram here. This can get kind of messy. Now, what causes this sinusoidal voltage? Let me show you where that comes from. I need a little room here. We're studying alternating current tonight. And remember, alternating current is where the current goes one direction and it stops, it turns around, goes back the other direction, stops, turns around, goes back the other direction. It just goes back and forth. 60 times a second in the United States. In Europe, it's 50 times a second. Let me talk about this omega for just a minute. This omega is called the angular velocity. It's the angular velocity of your phasor, and it's equal to 2 pi f. Now, in the United States, that's 2 pi times 60 hertz, which is 1 over seconds. A hertz is 1 over a second. Well, if you multiply that out, I get 377. And what it is, it's radians per second. See, radians are dimensionless. Do that, make sure I did that right. Take 2 times pi times 60 and tell me what you get. 2 times pi times 60. Do you get 377? And I want to hear an uh-huh.
Yep.
Yeah, that's right. So a typical voltage in the United States would be, what I said earlier, what was it, 155? I lost track of what I was doing there. Is that what I said, 155? I think that's right. 155 sine of 377t. If you plot that up, you'll get a sinusoid, just like we had. You'll get a sinusoidal voltage, just like we had. And the period, this whole thing here from start to finish is called a period. So here's your time, and here's your volts, and one complete cycle. See, the way we measured it in lab the other night, do you remember that? We had these peaks. Yeah. And the way we measured them in lab, we went from peak to peak. Well, that's the same thing. That's one period. That's one period. Or you could go from the bottom to the bottom. That'd be all right. That's one period. And you know how long that is? It's 1/60th of a second. That's not much. Let me see how much that is. 1/60th of a second. You know what that is? That's 0.016, a bunch of sixes, seconds. Not much. It wiggles pretty fast. That's one period of our alternating voltage. Where this 377 is the omega. It's the angular velocity in radians per second. If you had your phasor spinning around, here's your voltage phasor, and it's spinning around 377 radians per second, then the projection in the vertical direction, which would give you the sine, will give you the voltage. The voltage would equal to the maximum voltage. They call that the amplitude. I couldn't think of the name of it. This right here is called the amplitude. Amplitude. There we go. Now, if you go from peak to peak, they call that peak to peak. Peak to peak. Is that how you spell peak? I think so. Because the other way is P-E-E-K, right? And that's when you're playing hide and go seek. That's how you spell peak, I think. Yeah, peak. Well, see, that's the peak. It's like the top of a mountain. Top of the mountain, peak. Yeah, but that's not a peak. There's one there. Now, I want to show you where they got this. What causes this thing? Well, I'll tell you what. It's the generator at the electric company. Now, I'm gonna make our generator very simple so we'll understand it. But over at the electric company, that's where you get your electricity from. See if I can draw you something here that might make sense. if you had a current loop, we'll take a current loop. There we go. And we'll put it in a magnetic field. And basically that's what they have. That's what an AC generator is. There's a picture of an AC generator in your book. I should show you that. Let me see if I can find that. Hang on one tiny minute. There's a wonderful picture of an AC generator in here. Oh boy, I don't know if I can find it though. Okay, I might have to look some more. I'm not quite ready to give up yet. Let me go back here and look under maybe AC or motors or generators. Let me see if I can find it here. Just a minute. Motors. Do they have motors? No. Yeah, they do. 515. Let me look on 515. Well, that's not a picture of an AC generator. Dang it. Okay, I give up. It's in there, but you know the flux. Here's your area. This coil has an area, and it has an area vector. That's your area vector. It has the magnitude equal to the area, and the direction of it is perpendicular to your area, and your magnetic flux is equal to BA. But see, we're going to spin this thing. We're going to spin this thing, and if you want to take different angles, do you remember this is, it's really a dot product. Flux is a dot product. And so you could write this as BA sine of the angle between them. Sine of the angle between them. Now, if you want the derivative of the flux, Faraday's law says the voltage is equal to a constant, namely the inductance, times the derivative. Okay, well, let's find the derivative of this. Well, the derivative of this is BA cosine of theta. Isn't the derivative of the sine the cosine? But you have to use the product or the chain rule, and you have to multiply by d theta dt. Well, you know what that is? That's omega. That's what omega is. It's d theta dt. So the voltage is equal to minus L B A omega cosine of theta. Well, the cosine curve is a little different, but it's similar. That's the cosine of an angle. And this is this could be your voltage. This is just a constant. It's just equal to the maximum voltage that you would have. It would equal to the inductance times the magnetic field times the area of your coil times the angular velocity. That's where you get these sines and cosines. You have a rotating. You have a turbine, and the turbine turns the generator. They burn some coal. They send steam through the turbine. It spins the turbine. The turbine's connected to the AC generator. It's a coil that rotates in a magnetic field, and you get a voltage from it given by, well, this is a form of Faraday's law. No, this is an N there in Faraday's law. I'm thinking of this one here, but it's the same sort of idea. Now you know where they get the sinusoidal shaped voltages and currents. They get them from the AC generators. It's a coil spinning in a magnetic field. It's really an electromagnet. Okay, well, that was fun. Any questions so far?
So is that an N or an L everywhere there? I'm confused now.
There's an N here, but there's an L here. This has got current and that's got flux.
Okay, but after the equal sign on the flux one, is that supposed to be an N?
That's
So
supposed to
right
be
there on that line, after the equal sign to your right.
Oh, this one.
Yeah, is that supposed to be an L?
That should be an N. I was wrong.
Okay, I'm just confused. I was making sure.
Phoebe gets a thank you point right up there. Good going, Phoebe.
I'm just checking.
Keep me honest. I appreciate it. Okay, now we're going to talk about capacitors and inductors. So I'm gonna erase all this. I hope some of that made sense. Well, maybe we better go back to resistors for just a second. Now, if you have an AC voltage and it's acting on a resistor, and here's your voltage, you get some maximum value times the sine of omega t. There you have it. And here's a resistor. And you'll get a current in the circuit equal to this maximum voltage divided by the resistance times the sine of omega t. And they will follow each other. If you plot it up, they call this the time domain. And you put the voltage here. That's the voltage. Then the resistance will be like this. They just kind of tag along and follow each other. If you write this as phasors, see, this has got voltage and resistance. We're plotting them both together on the same graph. But if you do it as a phasor, here's your current. Probably should call that capital I, because it stays constant. It just rotates is all. It spins around in a circle. And here's your voltage. These are the phasors, and they spin around with an angular velocity of omega, which is, if you're talking about what you got in your house, it's 377 radians per second. They call this the time domain when you take a class in this stuff, and they call this the frequency domain. I don't know why they call it that, but when you see those terms, this is just a different way of representing this. I think this is a lot simpler than that. Now that's with resistors, but now let's talk about a capacitor. Let's suppose that you have a capacitor and you hook it up to a AC voltage. There you go. And here's the capacitor. Again, we can put that same AC voltage right here. It won't change any. It's the same deal. There's the voltage, and you can plot voltage versus the time here. But what about the capacitor? Well, of course, it has to have the same voltage, but how do capacitors work? They go V equals Q, no. C equals Q over V. Yeah, that's how they go. You got that memorized, don't you? So see, V is equal to Q over C, isn't it? Yeah, V equals Q over C. So in this case, what we have is V sine of omega t. That's what the V is equal to Q over C. Well, okay. Tell you what, let's take the derivative of both sides. You can do that in math, you know, as long as you do it the same to both sides. If you take the derivative of this side, you get V cosine of omega t times omega. Do I need to explain the chain rule to anybody? I hope not, but I'll be glad to. Okay, now when you take the derivative of this side, what you get is the current over the capacitance, because dq over dt, that's equal to current, right? By definition. And C is just a constant. So the current then, it doesn't follow like it did with the resistor. It's equal to C V omega cosine of omega t. I did a little algebra step there. I went from here to here. I didn't lose you, did I? If I did, just speak up. Okay, well, let's see if we can plot that. This is just a magnitude, you know it? That's just a magnitude, and that's a cosine. So let's plot that. Cosines kind of go like this. Remember the cosines look like that? Okay, now wait a minute. I think I'm goofing up here. Just a second. I got to think. I think I'm goofing this up. See, this would be the current. No, that's right. I believe that's right. Yeah. Hey, they're out of phase by 90 degrees. Can you see that? The current and the voltage are out of phase by 90 degrees. And it looks like the maximum current is equal to CV omega. Okay. Well, we'll do an inductor next. Do we have room over here? I think maybe we do. Wait a minute. Let's draw the what they call the frequency domain on it. Here we go. Need a little room here. We're going to draw the frequency domain on it. We're talking about the rotating vectors here. We'll say this is the sine, this is the voltage phasor, and it's spinning around. It's going around in a circle. There it goes. It's going around in a circle. But the current the current is 90 degrees ahead of it. Here's your current phasor. See, it's 90 degrees ahead. They're both spinning this way, but this is out ahead of it by 90 degrees. See, this peaks out at 90 degrees before that peaks out. See, this peak here is here. This doesn't happen till later. See, time is ticking away going this way. This is later. Here's where we get older, we get gray hair and like that. Here's where you're younger over here. This is early, see. The current leads the voltage. The current leads the voltage. In a capacitor. And there's your phasor diagram. Now, do they have that in your book? Let me look and see. Let me dig around. Oh, here's the phasor diagram that I partially erased on page 673. You see this phasor diagram here? That's for the resistor. Now let's see if they have one for the capacitor. Yeah, there it is. I got my colors mixed up. They did the voltage in red and the current in blue, but if you look with me on page 674, you got your voltage here and your capacitor here, or your voltage here and your current here, and they're 90 degrees apart. And these vectors called phasors. Actually, that's a voltage phasor and that's a current phasor. They're spinning around with an angular velocity. Well, in the voltage that we're using in our homes, it's 377 radians per second. Now we're going to do an inductor, but first, are there any comments or questions? Well, I got a bad feeling that maybe if you've never seen this before, it's kind of weird looking. Let's do an inductor. Now there's an inductor on page 675. And I just need room to do it. I hate to erase my resistor, but we're going to say goodbye to it. And we're going to do an inductor here. Okay, we're looking at an inductor now. Now here's your sinusoidal voltage. And there's your inductor. And if you used Kirchhoff's law and you went around this circuit, let's say it's some particular instant in time, this is plus and this is minus. Now a 60th of a second later, it'll switch. This will be minus and this will be plus. See, it goes back and forth 60 times a second. But if Kirchhoff is right, then if you go up a certain amount of voltage, V, then you have to go down a certain amount of voltage that way. And so the total voltage will be like this, using Kirchhoff's voltage law that we know and love. And we know what that is. It's minus L di dt. We've done that. And it's equal to 0 if you add them all up. Okay, well, great. Well, the question is, what's the current? we need a current that will obey this equation. And it turns out, if I remember right, it turns out to be minus the total maximum value times the cosine of omega t. Let me plot it up for you. I'm trying to remember what this constant is. It is I think it's a V over omega L. If I remember right. Okay, let's see if this works. Let's find the derivative of this thing. Now, the derivative of this thing would be, these are all constants. They'd just be minus V over omega L. But what's the derivative of the cosine? Does anybody know? Derivative of the cosine.
Sine?
I think it's the minus sign. Does that ring a bell?
Yeah.
It's the minus sign. And so you have a minus sign. And you'll have to multiply by omega because of the chain rule. There's two minuses. Hey, the two minuses make it go bye-bye. And now if you put a minus just a minute, I was doing great. Yeah, up here. Yeah, up here. We've got V sine of omega t minus L times V over omega L sine of omega t times omega. See, the omegas cancel, the L's cancel, and by Jove, that's equal to 0. That's it. I think you're looking at it. Well, let's draw it up and see what it looks like. We got room here, I think. Here we go. And now here's your voltage again, the same voltage we've been playing with all night. There's the voltage. But see, the current is these are just all constants, is a negative cosine. Well, that looks like this. A negative cosine looks like this. It's a negative cosine. And this is the current. Do you notice that the voltage in black leads the current by 90 degrees? If you were to draw the phasor diagram, it would look like this. If this is the voltage, see, the current is what they call lagging. It's behind. Here's the current. It's 90 degrees behind. They're all spinning like crazy with an angular velocity of omega. Now see if you can find, yeah, look on page 676. Page 676 in your book. Do you see this diagram? They've got the voltage here, the current here, they're spinning. Now, I had a student one semester that suggested a way of remembering how these diagrams work. He said, You know the voltage in a resistor and the current go along with each other. They're in phase. So we're going to say for a resistor, we'll call it the rabbit. You've got a rabbit spinning around in a circle like that, chasing, in the case of the inductor, they're chasing the lattice. L stands for lattice. The rabbit's chasing the lattice. Now I erased it, doggone it. Here, I'll put it back in here. Here's the voltage. And here's the current. And the current in an inductor has a phasor that's leading the voltage by 90 degrees. It's like the rabbit is chasing the lettuce. That's kind of crazy, but it helps. But see, in a capacitor, what you got down here for a capacitor, we did the capacitor, the current is leading the voltage. Is that right for the capacitor? Yeah, see, the voltage doesn't happen until later. The current's out ahead, it's leading. And no, I'm getting all mixed. I think that was the inductor. Guys, I got all confused. I was doing fine for a minute, but now I'm all confused. Which one is this? Is this the capacitor? And that's the inductor?
It's the other way around, I think.
Okay, now which one is this?
That's a capacitor, I think.
Okay, this is
Someone
the
can correct
capacitor.
me, but-
Okay, now just a minute, let me think. No, I think this one's the capacitor.
Yes, that is the capacitor.
And this one's the inductor.
Yeah.
And in the inductor, it turns out that the voltage leads the current by 90 degrees. And see, the voltage and the current in the resistor are in phase, but the current is lagging behind, is trying to catch up. And this stands for the coyote. This probably didn't make any sense yet, but it will. You've got the coyote here, the rabbit here, and the lattice here for the inductor. Well, we've tried to show you those. And there's one other thing before we work some problems, and that's what they call impedance or reactance. Let me see if I can introduce reactance, and then we'll just need some room. Here's some room. We know what the date is. It's the 17th. We know we're in physics. Oh, no, I erased somebody's thank you point. We don't want to do that. Now there's capacitive reactance and inductive reactance, and there's resistance. We know that's called resistance. This is called capacitive reactance. It's in ohms. Is all that coming out on? Pretty much, I think you can see it. And this is called inductive reactance. What it is, it's opposition to current. See, resistance is opposition to current. Capacitive reactance is opposition to current. And what it is it's your maximum voltage divided by your maximum current. Well, that's what resistance is. It's your maximum voltage divided by your maximum current. And that's what inductive reactance is. It's your maximum voltage divided by the maximum current. Okay. Now you understand that, but what is the equation for capacitive reactance? Well, now let's see. We did the capacitor, and we had it here, but I lost it. Here it is. You know what? This sure looks like the maximum current to me. When we did the capacitor. So if you want the capacitive reactance, it'll be the maximum voltage divided by the see, that's the maximum voltage hiding in there. And look, that cancels out, and what you get is 1 over omega c. That should be the equation for capacitive reactance. Let's see if we can find it. I don't see it. Yeah, there it is. This is on page 674. That's the equation for capacitive reactance. It's in ohms. Now, what is it for inductors? Gee, I don't know. Here it is. Look. You know what this is right here? This is your maximum. No, that's not it. Here it is. Look here. Do you see this right here? That's your maximum current. So your inductive reactance, this will all make sense in a minute. I'm going to write the inductive reactance for you. What it is your maximum voltage divided by your maximum current. It'll be in ohms, and this is going to be your maximum voltage divided by this thing, which is your maximum voltage. Never mind this minus sign, make it a absolute value sign. There you go. And this will be divided by omega L. And so when you do this, the voltages cancel out and you're left with omega L. So let's summarize. We're going to summarize. We're talking about resistance to current. Capacitive reactance is equal to 1 over omega C. Inductive reactance is equal to omega L. Resistance is just resistance. You don't have any fancy formulas for it. It doesn't depend on your omega. Once you've built this resistor with so much wire, that's it. You've got the resistance. Now let's look at the units for a minute. Let's see if these work. These things are in ohms. We're going to see if this works. What is omega in? Well, it's radians per second, isn't it? So that's what, seconds to the -1? Capacitance is in farads. So that we'll put that in farads. Somehow we've got to show you that this is equal to ohms. Well, we can do it. What's a farad? Well, a farad is a coulomb per volt, right? So we'll put a coulomb here, and we'll put a volt there. It's a coulomb per volt. We'll just put the volts in the numerator. And what we got here is coulombs per second. Well, a coulomb per second is an amp. So what we have here is volts over amps. You know what? That's equal to ohms. Hey, that thing worked. Now let's do this one. This thing has a name. We'll see. I'm going to see if anybody's awake. This is pretty boring. I apologize for how boring this all is. But hey, you like electricity, right? You like it.
Yeah.
Yeah, we all like it. And so it may be boring, but let me go to my friend Zach. Zach, we'll see if he's been listening. This thing right here has a name, Zach. What's the name of it?
Inductive reactance.
He's got, by Jove, he's got it. It's inductive reactance. Good going. And while I've got Zach on the line, Zach, what's the name of this little guy right here? It's a Greek letter omega.
Oh, right. It's always so sad.
It's omega.
Yeah, but what's the name of it? Besides omega. It's got a fancy name.
The angular velocity.
That's it. It's angular velocity. Good going, Zach. And Zach, I'm picking on Zach right now. This L, that has a name. What's the name of it?
The inductance.
That's it. Zach knows it's inductance. Now let's make sure that this stuff works. Now that's called capacitive, or no. Inductive reactance. It's in ohms. See, all of these are in ohms. Resistance is in ohms. Capacitive reactance is in ohms. Inductive reactance is in ohms. They're all in ohms. We're talking about a resistance. I shouldn't use the word resistance, so that's a bad term. Opposition. These things are all oppositions to current, okay? You're trying to run current through something. Something's opposing that current. Now, resistance will do it, but so will capacitors, because once they start filling up, they don't want you to put any more current in them. They say, sorry, the N is full, there is no more room, go away. The capacitor is full of positive charges, do not come back in. We're trying to have, what do they call it for a COVID, where you space people out, distance, what do they call that? Distance spacing. Don't know what they call it. All right, here we go. We have ohms there. We have radians per second there. Okay. And we have henries. Do you remember inductance is in henries? Now, somehow we got to get this to work. Well, if you remember this, I showed you this one night. A henry is equal to ohm times a second. Got it made. Look, 1 over seconds, and the seconds go bye-bye, and you're left with ohms. Yay, we did great. Well, we need to actually work some problems because we kind of got overloaded on theory tonight. Maybe if you read that stuff over, it would make a little sense to you.
I don't know. Why is it a different Imax when you do the inductive reactance? Like where I'm not understanding where that came from.
Oh,
I see where it came from, but I don't understand where that equation came from.
well, now these here are definitions. Inductive reactance, by definition, is your maximum voltage divided by your maximum current.
I guess I was asking you.
Where we got that? You want to know where we got that current?
No, yeah, but you use negative voltage divided by omega L. That equation right there, where did that come from?
Okay, now just a minute. You lost me now. This equation here?
No, the one to the left of that.
This one here.
Yes, that one.
Where did that come from? Well, I'll tell you where it came from. I'm so glad you asked. We did it, but It just kind of snuck by me. But let's go back over it real quick. We'll go back over it. We did
I know
a,
you had, but I forgot.
no, that's okay. We did a KVL around this loop. I remember doing that. And if you go from here to here, you get V sine of omega t. And then here, it has to be negative minus because, well, when you're in parallel, the voltages have to be the same. And it's minus L di dt. And I think you're okay with that, Phoebe.
Yes.
You're okay with that. And what this is a first order differential equation. And when you solve it for current, now I have to stop and think.
Oh, I see. I see. I look back at my notes and I see where we got it from. I'm sorry.
No, that's okay. It's I think it's minus V over, yeah, it's this. Yeah, this is exactly what it is.
Okay.
When you solve this equation, which is a KVL thing, and you solve it for current, you get this. Well, this right here is your maximum current. So what we're going to do is we're going to take our maximum voltage. There's some room right here. We're going to take our maximum voltage and we're going to divide by this maximum current. Never mind the minus sign. We just want the amount because it goes up and down all the time. And it's got a maximum voltage divided by omega L. And when you do that, you just get omega L. That's where it came from.
Okay. Thank you.
Oh, anytime. One last thing, and we're going to take a little 10-minute break, and then we're going to work problems. It's possible that you might have a circuit like we'll work with Thursday night that'll have it'll have a voltage source. You know, V equals some maximum voltage sine of omega t. And it's possible you might have one that has a resistor, an inductor, and a capacitor. You might have all three, or just maybe two of them. We'll do different ones. We'll hook different ones together and measure them. Here's your voltage. Now, if you did the phasors, what you'll get is you'll get your inductive reactance, you get your resistance, and you get your capacitive reactance. Now, this might be little, it might be big. It kind of all depends. We have the equations. They go like this. We just need some values to plug in to learn how to do it. But these are all ohms, aren't they? But see, these are opposing one another. When you plot these up in what they call the time domain, if this is the voltage, if that's the voltage, then the current in the inductor, I'm trying to remember which way that goes. The current in the inductor, I believe, goes like this. There's the current in the inductor. The current in the capacitor goes like this. This is the current in the capacitor. Do you see the current in the capacitor and the current in the inductor are 180 degrees out of phase? That's why we draw them like this. This is the inductive reactance, this is the capacitive reactance. They're 180 degrees apart. Now they may not be equal. This might be really short, like that. We don't say short, we say altitude challenge. There we go. Or it might be much longer, and this one might be the altitude challenged one here, see? It all depends on what these values are. But these things are vectors. They're called phasors, and they add like vectors. And after our 10-minute break, we're going to add them like vectors. You remember how to do that. If these things are opposing, you have to subtract them. And what you'll wind up with is a vector about that long. And these two, we've subtracted them. Well, we've added them vectorially, you understand. And then when you add this vector here to it, what you'll get is this vector here. They have a special name for that. It's called the impedance. The symbol is Z. It's called impedance. And we're going to work some problems here after I go see what's in the refrigerator. Go stretch for 10 minutes. We'll be back. And we're going to work some problems with impedance. Okay, go stretch. Oh, I needed to stand up. I'll give you 10 minutes. We'll be back. Hey, how did my buddy do a basketball tryout? Oh. Leave the porch light on? Leave not on. Well, we better get going, I guess. I wonder if I still have a class. Let's see. Yeah, we're still here. Tonight, I'd like to talk about power. But first, let's go over some of this stuff here about reactants. I looked out, I went downstairs, and everybody was having pancakes and bacon and eggs. So I got me a bite. That was pretty tasty. Let's suppose that we had a circuit like this. You know what that is? That's a RLC circuit or a LRC circuit. What do they call it? I'll look it up. They call it a RLC circuit. That's what that is. we have an RLC circuit. And I just made up some numbers for you. Suppose this is 2 henries. Now I'm going to put the henries in brackets because that's a unit. I don't put the L in brackets because L is not a unit. L is a name for the inductor. It's called inductance. The capacitance, I'll say, is 4 microfarads. See, the microfarads, that's units. You put those in brackets. The capacitance, the C stands for capacitance. It's a variable. If you put C in brackets, you know what that is? That's coulombs. You don't put that C in brackets, that's capacitance. And I'm just making this up. So suppose this is 500 ohms. We put the ohms in brackets because it's a unit. And suppose the voltage is a wall socket voltage of 155 volts, sine of omega t, where omega is 377 radians per second. Remember where we got that? Omega is 2 pi f, and f is 60 hertz. Hertz is a unit. It goes in brackets. And if you multiply that on your calculator, you'll get 377. So we know all of our facts now. And now we're going to draw what they call the impedance diagram. Okay. And we'll find the current. And we'll find the voltages. It'll be fun. You'll like it. Now what we're going to make now is called an impedance diagram. It's very much related to the phasors that I talked about. Remember phasors? Let me ask somebody. We'll see if anybody's been listening. Nicholas, I'll pick on my friend Nicholas. Nicholas, what is a phasor? What's a phasor?
Well, I don't know. Something to do with your something lag in voltage or something.
Yeah. You're kind of bouncing around the idea there. Let me tell you what it is. A phasor is a rotating vector. It represents it can represent voltage or current. It can represent current. It rotates with an angular velocity omega. That's what a phasor is. Now the impedance diagram has reactances. They're very much related to the phasors. I'll show you the relationship. But now the next time, Nicholas, I ask you what a phasor is, you're going to know what it is. It's a rotating vector. That'd be enough for me. It's a rotating vector. Okay, now we're going to do the impedance diagram. Now you put your inductance here, inductive reactance here, and your capacitive reactance is opposite down here, and the resistance here. This is the standard position for your impedance diagram. Now this is 500 ohms. It's given. But to find the inductive reactance, you have to use this formula. It goes like this. Now I'm going to shut up for just a minute, and I want you to find the inductive reactance. And we'll put the number in here. I'll be quiet. You find it. Why should I have all the fun? And this is wrong. This is wrong, by the way. Inductive reactance is omega times L. Capacitive reactance is 1 over omega times C. Sorry about that. Somebody could have gotten a thank you point just then, but nobody got it that time. Okay, find the inductive reactance. I found it. Somebody tell me what they got.
754 ohms.
That's what I got. I got 754 ohms. We drew that about right. Maybe this is a little shorter. We try to do this to scale, see? Get your ruler out. If this is 500, that kind of looks like 754, doesn't it? Now let's do the capacitive reactance. Go ahead and do it for me.
$663.13.
She's faster than I am, but I think that's what I got. I got 663.13. Now I need to draw that a little longer than the 500, but a little shorter than that. It's pretty dang close to what it is. It's maybe, I don't know, maybe more like this. I really need my ruler to get this right. Now, is that showing up? Yeah, that's showing up. It's 6. Phoebe, let's just round it off. 663. There you go. We're doing great. Now, these act like vectors. And see, these are opposing one another. So what you can do is you can subtract them. Let me do that over here. 754 minus 663. Did I do that right? Is it 91? I think it is.
Yep.
So you have a 91, just a little small guy right here. It's 91. Now this right here, when you add these two vectors, you get the impedance. I tell you what it is. It's the square root of 91 squared plus 500 squared. Now let me do that. 91 squared plus 500 squared. Did you get an impedance of 508? 508.2 ohms. See, this is 91 ohms when you subtract those. And then you have to use Pythagoras to get the impedance. We have the impedance, folks, 508.2 ohms. The interesting thing is the inductor and the capacitor almost cancel each other out. Kind of interesting. They almost cancel each other out. Okay, now let's get the current in the circuit. Now here's how the current works. The current in the circuit is going to be the voltage divided by the impedance. Well, what's the voltage? Well, it's 155. What's the impedance? 508.2. We can get the current in this circuit. Well, we'll get the maximum current. Remember now, this is AC. It goes back and forth, back and forth. Well, I think I got the current. I think it's 0.30 rounded off to 5 amperes. You know what that is? That's 305 milliamps. We can measure that. We have ammeters in the lab that would measure that. And remember, it's going back and forth, back and forth. Now we can get the voltages everywhere. If you want the voltage on the resistor, V equals IR. We've got the current, we've got the resistance. So give me the voltage on the resistor. Go ahead. Somebody tell me the voltage on that resistor. Stephen, do you have that voltage on that resistor?
Not yet.
Take your time. V equals IR. The current's 0.305. The resistance is 500. What do you get for the voltage? I think I'm going to put it in red. I like voltages in red. Well, I got an answer. How about you guys? What did you get for the voltage on the resistor?
152.5.
That's what I got, 152.5 volts. $152.5. We did good. Now let's get the voltage on the inductor. Now the way that works, well, it's the same deal. Only it's not an R anymore. It's the voltage is equal to IXL. It's still amps times ohms, but it's not a resistor, it's an inductor. But the voltage is equal to IXL. Well, what's XL? Oh, there it is. So get the voltage on the inductor, go for it. Well, I got what I think it is. What do you think it is? What's the voltage on the inductor? How about my friend Phoebe? Phoebe, what'd you get for the voltage on the inductor?
It's 229.97 volts. You could
Yeah,
round it to
that's-
230 again.
I'm just going to round it off to 230. volts. So we got the voltage on the inductor. Now let's do the capacitor. How do we do that? Well, that's not a problem. We just go V equals IXC. And XC is, I don't know where to go. Where's the capacitor? Oh, here it is. See it? Can you guys see that down there in the bottom there? It's 663 ohms. So get the voltage on the capacitor for me, please. I'll tell you what I got. I got 202. I'll just, it's 202.2, but I'll just say 202. That's good enough. 202 volts. Now, this voltage here is 155 volts. It looks like Kirchhoff's law doesn't work so good. Because if you take 152 and 230 and 202, I don't think you get 155 out of that. But remember, these two are fighting each other, and you can make a voltage phasor diagram. You know what we did to get these numbers? We just multiplied by the current. In series, the current is the same everywhere. So let's do our voltage phasor diagram. There's room up here in the corner. Let's do that. We're going to do our voltage phasor diagram. It looks just like this. It's just you're multiplying each one of these by the current. And what you'll have is, you'll have the voltage on the inductor, which is 230. You'll have the voltage on the capacitor, which is 202. It's a little bit smaller, not much. It's 202 voltage on the capacitor. You'll have the voltage on the resistor, which is 152. Maybe like that. A little bit longer, maybe. Maybe like that. This is the voltage on the resistor, and it's 152. And you can even put the voltage of the source, and I'll show you how. See, these are subtracting. What's 202 from 230? Is it 18 or is it 28? I think it's 28. See, when you subtract these, you get 28. This is 152, and if you square that, remember, these are vectors. Do you understand? When you subtract these, you'll get 28 going this way. It's very small. It's a 28. And when you square that and take the square, do that. Square that, take the square root. Let's see what we get. 28 squared plus 152 squared square root. Oh, boy, you. You know what I get? I get 155. Well, that's the total voltage. See, that's right here. This is your total voltage. It's equal to 155. When you square this, don't you get 155 roughly if you round off? I think we rounded off a little bit. Now they have a name for this little angle right here. See that little angle? That little angle is called the phase angle. We can get it. There's several ways. Let me make some room here. We'll find out what that phase angle is. It's well, if you use the cosine of that phase angle is 500 over 508.2. You could do it with the cosine. Or if you did it with the sine, you could say the sine of the phase angle is 91 over 508.2. You should get the same angle. Or you can do the tangent. The tangent of the phase angle should be 91 over 500. Do it all three ways and let's see if it comes out the same. It better, or we must have done something wrong.
Are we doing it on the reactances or
Yeah.
on the voltages?
You can do it on either one. Now, what am I
Okay.
doing? Am I getting mixed up here? I'm doing it
Just
on
all
this one.
reactances. Yeah. Okay. Thank you.
Thank you for asking. We could do it on here. You know what? It should come out the same. We'll do that in a minute. Go ahead and do that. Let's see if it works. I get 10.3 degrees. I'm getting 10.3 degrees, but let me do it both ways and let's see. Yeah, hey, I'm getting 10.3 degrees doing it this way. And boy, Joe, I'm getting 10.3 degrees. But like Phoebe said, you could have done it with this. You could have gone, my problem is having room to do it in. Okay, let's do it up here. If you did it up there, then you could go the tangent of the phase angle is 28 over 152.5, right? Yeah, try that. Well, I got 10.4 degrees, so I must have rounded something off someplace. Well, let's try another one. If you do the sine of your phase angle, that would be the 28. I think I'm rounding off something. Divided by the 155. Let's see what that is. Well, I'm getting 10.4 degrees. And finally, you could go the cosine of your phase angle. If we were more careful and if I didn't round off so much, they would be precisely correct. The cosine is going to be 152.5 divided by your 155. Let's see what that is. That's the cosine. Yeah, now that one comes out to be 10.3 degrees. The phase angle is 10.3 degrees. So so what? Well, we have the phase angle, and we know that the voltage and the current. See, the current will be in phase here. The current and the voltage and the resistor are in phase. Here's your current. It's in the same phase as the voltage of your resistor, but your total voltage in your circuit is leading the current. Now, that's because this is the inductor is the dominant component. See, the inductive reactance is bigger than the capacitive reactance. Where's the capacitive reactance? I got lost. Here it is. See, the inductive reactance is 700 and something. Capacitive reactance is 600 something. This is an inductive circuit. Now, to help you to remember this, there's this old saying called Eli the Iceman. Eli the Iceman. Now, have any of you ever heard of that saying before? Any of you? Eli the Iceman, have you heard of it before? How about Stephen? Stephen, have you heard of that Eli the Iceman saying before?
Nope.
Well, that's okay. You're going to hear it in a course called what is that electrical course that we teach that I haven't taught for years? It's called electrical science. Stephen, are you going to take electrical science?
Not that I'm aware of.
You are. You may not be aware of it, but you're going to take it. You all are. Everybody has to take electrical science. How about Zach? Zach, did you know that you have to take electrical science?
No.
Well, I hate to bring bad news, Zach, but you're going to have to. Come on now, who else we got? Hey, Phoebe, did you know that you're going to take electrical science?
I might not, since I'm going towards biochemistry, but it sounds interesting.
You know, I would suggest you do, because biological things like frogs and people, I think they got electricity going on.
Yeah.
I think with your heart, hey, bum,
Oh, yeah.
bum, bum. I mean, there's electricity going on. Nicholas, have you ever heard of Eli the Iceman?
No.
Okay, well, here, let me tell you about Eli the Iceman. What it says is E, that stands for EMF or voltage. The voltage leads the current. The voltage leads the current in an inductor. See, that L stands for inductor, and the C stands for capacitor. And this says that the voltage leads the current in the inductor. Okay, now let me find my, here's the current, and here's the voltage in the inductor. Oh, look, it's leading. It's out ahead. See, think of this as the rabbit. Here's your current, and the rabbit is chasing the lettuce. There you go. And the voltage in the inductor is leading the current. Now, ice, the current leads the voltage in the capacitor. C stands for capacitor. See, here's your current, and here's your voltage in your capacitor. That's the coyote. C-O-Y-O-T-E. The coyote is chasing the rabbit. And here he goes. But the rabbit's out ahead. He's leading. He's leading. Now, if you plotted up the, what do they call it, the time domain. Let's do the time domain. There's room down here. We'll do it down here. It really gets messy, but we'll try. We're going to plot up voltage and current versus time. And we know we have the current. And we know it's a sinusoid, and here's the current. There's your current in your circuit. But the the voltage in the inductor is out ahead by 90 degrees. So I don't know what color to use, maybe blue. Here's the voltage in the inductor. This is in blue. And that's the voltage in the inductor. And see, it's the voltage in an inductor leads the current by 90 degrees. Here's the current, and here's the voltage in the inductor. See, and the voltage in the inductor peaks out right here. But the current doesn't peak out till later. See, going this way is later. You understand that? Time is ticking away going this way. Time is getting longer this way. We're getting older. But the voltage peaks out before the current. And looky here, the voltage comes down here and crosses the axis here, but the current doesn't come down here and cross the axis till later. So the voltage leads the current in the inductor. Ta-da, we got that. Okay, well, let's do the voltage in the capacitor. I've got some green here. We could use it. Voltage in the capacitor. Where are we? Here we are. That's the coyote. Well, the current leads the voltage in the capacitor. Here's the current. The voltage in the capacitor is like this. We'll put it in green. There. This green thing, I don't know if you can see green on there. Not very good. Dang. But I'll make it darker. This dark green thing is the voltage on the capacitor. It's the voltage on the capacitor. See that the blue one is the voltage on the inductor. Did the blue even come out where you guys can see it? See, this is supposed to be the voltage on the inductor. You see how they're button heads? But it turns out, I didn't draw it very good. The capacitor is really smaller. Not much smaller, 202 volts, and this is 230. I should have made the voltage on the inductor a little bit bigger. Here, I'll make it a little bit bigger. Let me get my blue, though. I'll try to make it a little, come on, blue. Yeah, we'll try to make it a little bit bigger. There we go. See, that's the voltage on the inductor. It's bigger. It's 230, whereas the capacitor is only 202. And here's the current. which is on a different kind of scale altogether. It's 0.305 amps. Now let's do the total voltage. The total voltage it's a sinusoid, but it's off by a tiny amount of 10.3 degrees. And it's it's leading the current by 10 degrees. See, the inductor voltage is leading the current by 90 degrees, but the total voltage is only leading the current by 10 degrees. Here, I'll try to draw it. It's like this. Not much different than the current graph, but it's got a 10 degree. It's leading by 10 degrees. See, the equation for the total voltage goes like this. It's equal to 155 and the sine of omega t. Now, when a graph shifts slightly to the left like that, it's plus 10 degrees. Now, you should put this in radians, 10.3 degrees, which we could easily do. We could easily convert that to radians, but we'll leave it in degrees. That's your voltage on the whole thing. That's what's being supplied here. Well, we've done an impedance diagram. There it is, ta-da. We've done a voltage diagram. And we've even put the current phasor on that. This is a phasor diagram. And there's a phase angle there. And we did a problem. But you've just discovered that the current and the the voltage in a circuit like that, they're just not in sync. They're out of sync a little bit. See this red one here? That's the voltage in the current, and this black one is the current in the circuit. And they're both sinusoids, but they're out of sync by 10.3 degrees. Now I want to talk to you about power in an AC circuit. We've talked about power in an AC circuit, and you've even calculated it. Remember those light bulbs? Problems we had with light bulbs? You might not have remembered, but we had some AC light bulbs. We had a 40 watt and a... Well, I know we did an experiment with light bulbs. We had 60 watt light bulbs. I just had a senior moment. Well, I was going to talk to you about power in an AC circuit. So let me tell you about that. And we'll come up with our equation for power. And it's in your book. We could read the book. Let me show you where this is in the book. Before I do, is there any questions anyone has about reactances, phasors, impedances, time domain, frequency domain? Eli the Iceman. Any comments or questions? Okay, well, we're going to talk about power now. Now, this is in your book. It's in your book on page 580. No, 683. It's on page 683. Now, one last comment. This is called the time domain, and it's ugly and messy. This is the frequency domain. These are your phasors. These are your sinusoids. Don't you find these phasors easier to work with than the sinusoids? Amen? Well, I do. I think that these phasors are a little easier to understand than these sinusoids. That looks pretty messy to me. I'll ask somebody. Stephen, what do you think? Easier to work with, Stephen? The sinusoids or the phasors? What do you think? Uh-oh, coffee break. We'll go to my other friend, Zach. Zach, easier to work with, the sinusoids in the time domain or the phasors in the frequency domain? What do you think, Zach?
The phasers.
Oh, yeah, they're easy to work with, you bet. Okay, well, here we go. We're going to talk about power in an AC circuit. Somehow I need to get around to RMS, root mean square. There's just not enough time for this stuff, but you might have to read some stuff. There's some homework. You all know that there's homework. And you have a final eventually coming up whenever we said that was. Seemed like we said December 10th. Gosh, December seems like a long way away, but it's not. December 10th. I think that's right. Is that what we said? The final is December 10th? Let me make sure. I don't want to lie to you. This says, yeah, December 10th. Well, this is the 17th. Okay, well, it's 3 weeks and 2 days from now. 3 weeks and 2 days from now. Okay, we're talking about power now. We've introduced some ideas, and if you'll come Thursday night, you can actually plug in some components and measure voltages and currents. It'll be a lot of fun. The experiment is it's in content. Go to content and pull it up, and you can study it. Okay, now let's suppose you had suppose you wanted to find power. Well, they have what they call instantaneous power. And what it is it's current times voltage. And it's good at that instant. The thing about AC is the power is changing all the time because the current's changing all the time and the volts are changing all the time. And they'll be out of phase. Remember in that circuit we just did, the current and the voltage were out of phase by 10.3 degrees. They call it the phase angle. This is called instantaneous power. Instantaneous. I think that's how you spell instantaneous power. And you know what the units are for power. It's watts. And this is supposed to be amps, and that's supposed to be volts. And I like to put my units in brackets. You see, a watt is a joule per second. That's what a watt is. And an amp is a coulomb per second. That's what an amp is. And a volt is a joule per coulomb. The coulombs cancel, and boy, Jove, you've got joules per second on both sides. So the instantaneous power is like that. Well, if you wrote these out, you have your maximum current times the sine of omega t. And then you have your maximum volts times the sine of omega t. But you might have a phase angle to worry about. I don't know, call it theta or phi or something, give it some kind of name. So you've got, here, let's make it a minus. I think we had a minus in that problem we just did, if I remember. I don't remember. I shouldn't have erased it. I can't remember whether there's a minus or a plus. I think the current was a minus, and this was just omega t. That's what it was, maybe. It doesn't really matter. Now we're going to do some algebra now. You guys love algebra. I know you do. So we're going to write this as I max sine of omega t, V max. Now there's a trigonometric identity that you learn when you're in high school. It goes like this. Sine of omega t cosine of theta minus cosine of omega t sine of theta. Does anybody remember studying trigonometry in school when you were younger and better looking and running across this trigonometric identity? If you did, say, uh-huh. If you, yeah, he remembers it. Yeah, good. Okay, great. Well, we're going to do another algebra step. See if you can get to here with me. See if you can make it to here. That's supposed to say max. We're going to put instantaneous power is equal to I max. Bear with me, this is pretty boring, but we'll come up with a nice equation here in the end for power in an AC circuit. Whenever you buy an appliance, it tells you what the power is. So you're going to have I max, V max, sine of omega t times sine of omega t. Well, we could just square it. How's that? Times the cosine of theta minus sine of omega t cosine of omega t sine of theta. See if you can get to here with me. All I did was a little algebra there. Can you get from here to here? Can you make it? Because if you can,
So
we're
you
halfway.
just
Go ahead.
distributed sine omega t over that.
Yeah,
Okay.
that's all I did. Thanks for asking. Now here's something here I don't know if you're familiar with, but if you want the average of anything, like if you want the average power, what you have to do is you have to integrate power with respect to time from 0 to 1 period. And then you have to divide by 1 period. That's the equation for average anything, like rainfall, for instance. If you wanted the average rainfall, say for a year, well, you'd have 12, you could have 12 different, for each month. January, you'd have rainfall. February, you could have rainfall. You could add up the rainfall for each month, and then you divide by 12 if you're doing months. I guess if you're doing weeks, you'd have to divide by 52. And you'd get the average. This is just a formula for the average of anything. And in this case here, we're going to get what they call the average power. Well, it's going to be Imax Vmax divided by the period. Of course, we know if you're doing electricity in your home, it's 1/60th of a second. That's what the period is, 1/60th of a second. And here you would have the integration of sine squared cosine theta dt minus the integration of sine omega t. Uh-oh, I'm running out of room here. Am I going to make it? Cosine omega t sine of theta. I barely made it. There. I think that's legal. Oh, wait a minute. I need a dt in here. Stick a dt in there. I ran out of room. Put a little dt in there. And go from 0 to 1 period. All right, we're almost done. Now this one here is equal to 0. That's just a constant. The sine of that, 10.3 degrees that we had on our problem, you could pull it out. And what you have is a sine cosine. The integration of sine cosine is 0. Now, if you don't believe me, go talk to your math teacher, but it is. But this one here, you can pull that out. All right, we're almost done. So you're going to have Imax Vmax over the period times cosine of theta times the integral from 0 to 1 period of sine squared of omega t. And I tell you what that is. This integral here is equal to it's equal to 1/2 or 0.5 t. And now again, if you don't believe me, go to your math teacher, or you can work it out. You guys know how to integrate. We could integrate that. You guys have taken integration. And so if you do that, do you notice that the t's are going to cancel? This whole thing is 0.5 t. That t and that t cancels. And here's what you're left with. You're left with 0.5 I max, V max, cosine of theta. And you're, white Job, you're done. You're done. They have that formula in your book. Let's see if I can find it. By Jove, it's on page 685. If you look on page 685, you'll see this equation. Only they call it I0, V0. They're talking about the maximum. I don't know why they call it I0 and V0, but it's the same thing. What happened to the cosine of theta? Just a minute now. Something bad happened. Something bad. No, there it is. Yeah, there it is. It's on page 685, just like I said. 1/2 I max, V max, cosine. They didn't use theta. They used phi, but that's just a dummy variable. Put phi's in there instead of thetas. Here, let me write it the way they write it. Here's an important formula. This says that the average power in an AC circuit is 1/2 the maximum current, they call it I0 for some reason, times the maximum voltage times the cosine. Now they used phi for their phase angle. I use theta, it's just a dummy variable. Okay. Now I wish I had a little more time to explain the root mean square. But when we measure voltages and current in the lab, we are measuring root mean square. Let me make some room here and I'll show you what I'm talking about. For a sinusoid, the root mean square voltage is equal to 0.7071 times your maximum voltage. And the root mean square, and these are what's measured. The root mean square current is 0.7071 times your maximum current. This is what your voltmeters and ammeters measure. And I don't know if I got time to explain it right at the moment, but it's called root mean square. See, your maximum voltage is 155 volts in your wall socket there. And if you multiply that by 0.7071, tell me what you get. Do that. Do it. And tell me what you get.
109.6.
Yeah,
or
you're supposed to get
110.
you're supposed to get 110. I think let me change it just a minute. Yeah, what it really is, it's 155.6. There you go. I think maybe I rounded off bad, but you've heard of 110 volts. I know you have. It's a 110 socket. Well, see, that's the average. It's not the average voltage, it's the average, it's the root mean square voltage. The 110 is the root mean square voltage. But now if you put the root mean square voltage in there, what you'll have is 1/2 times 0.7071 times the root mean square current times 0.7071 times the root mean square voltage cosine of phi, the phase angle. And if you'll do that with me, tell me what you get. And did I do that wrong? Yeah, I did
What is
that.
the current?
No, this is wrong, guys. I'm sorry. You have to plug in the square root of 2. This is wrong. No, I did this right. I did that right. But see, the maximum is the square root of 2 times the root mean squared. That was correct. But see, the maximum is the square root of 2 times the root mean squared. And I'll have to tell you, I'll explain that Thursday night if you come to my lab. We'll explain the root mean square. And if you put that in there, see, that gives you the square root of 2 times square root of 2. That's 2 divided by 2, and you're done. Done, you're done. And you've got your equation for average power. Here's some room here. The average power is equal to the root mean square current, the root mean square voltage, times your cosine of your phase angle. They even have a name for this. They call it the power factor. The cosine of your phase angle is called the power factor. And you'll see that equation on page well, I don't see it. Well, they have one down at the bottom for resistors. See, if you have a resistor, there is no phase difference. The phase angle is 0 for a resistor. Cosine of 0 is 1. And I think you've used that equation before, P equals IV. But if you're in an AC circuit, P equals IV, they're both RMS, times the cosine of the phase angle. Don't think I've lied to you any. Important equation right here. Yeah, here it is. This is an important equation. Gives you your average power. See, if all you've got is an inductor, what do I have here? 3 minutes left. If all you have is an inductor, and you hook up that inductor, the phase angle will be 90 degrees. What's the cosine of 90? Does anybody know cosine of 90? What's the cosine of 90? Put it in your calculator if you don't know. Just stick it in your calculator. What's the cosine of 90?
0.
It's 0. If all you have is an inductor, the cosine of 90 is 0. There is no average power. There's instantaneous power, but every bit of energy that you're putting into this magnetic field is given back to you 60 times a second. And the average is 0. Because what you store up, you give back. You store up and you give back 60 times a second. The average power is 0. Same with a capacitor. If all you have is a capacitor, now it stores up energy and it releases energy 60 times a second. But the phase angle is 90 degrees. Now it's a negative 90 degrees, but the cosine of negative 90 is also 0, right? Is that right? I think so. So the average power on these circuits is 0. Well, we've given you an introduction. If you didn't understand everything, don't feel bad. Come Thursday night, you'll understand some more. I hope to see you all. It'll be fun. Any last comments or questions before we say goodbye? Here's your
I had a
chance.
question about Thursday night.
Yeah.
We got the email saying that all of the campuses were going to be switching to distance learning or whatever on starting tomorrow. Is that going to affect the lab?
I didn't get a thing that said starting tomorrow. I got a thing that said Thanksgiving. Is it?
We got an email that said starting November 18th, we were switching to distance learning. And I didn't know, also I had the same question.
Oh, really?
Yeah, I don't know though if it applies to our lab or not, but I thought maybe you would know.
Oh, really, guys?
I mean, I hope not, right?
I tell you what I'm going to do. I'm going to find out. I'm going to get on the email and read that. I want to have that lab. I think it'd be good for all of us to do that lab. And I want to meet with you Thursday night. But if they've closed it down, they've closed it down. They told me a long time ago that it was Thanksgiving vacation. And after that, there will be no on-campus classes. But maybe they changed it. I will put it in announcements. Okay, look.
Okay.
In the morning or tonight or in the morning, look under announcements and I'll say, I'm sorry, I'm heartbroken over it. I wanted to see you guys one last time, but we're going to do what the bosses say. But hopefully we get to go. Well, I'll put it on announcements. Read the announcements. Thanks for telling me. Anything else? Okay, well, I'm going to say goodbye for the night. Thanks for coming.
Alrighty.
Yeah, thanks for
Thank
coming
you.
by. Bye-bye.
Have a good evening.
Bye. You